Hey, good evening, Nikhil. It's 6 p.m. and we are supposed to start, but given that it's just you and I here, I say we wait for a few more minutes to see if anyone else is joining, and then we'll start. Yeah, good evening to you too. Thanks. Hi, good evening, and welcome to week three of the live sessions for the course Fundamentals of Additive Manufacturing Technologies. This course is taught by Professor Sajan Kapil, who is a faculty member in the Department of Mechanical Engineering at IIT Guwahati. And I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. Nikhil has posed a question. Apparently, he missed the previous sessions and he would like to know where he might find the videos or the lectures. So, Nikhil, in the NPTEL forum, you might find a sheet, a link to a sheet detailing the relevant YouTube playlist as well as the folder on which we share the session notebooks. So, you should be able to find it on the NPTEL website. In case you can't find it, please let me know, and maybe I'll share the link personally in the next session. And with that, we will start. Just allow me a minute to share my screen. All right. So we have been discussing tool path planning, and previously we also discussed other aspects of computer-aided process planning, such as slicing, support generation, and a brief introduction to overall AM technologies. This will be the last lecture in the module of computer-aided process planning, and it deals with tool path planning. And while you must have deposition across a specified toolpath, and you must plan a toolpath for the exterior contour, the interior contour, and the bulk or the area to be filled. We mostly focus on the area filling methods because that constitutes the maximum volume where the material is deposited. And in a way, we know that edge effects play a role such that the material properties and performance at the edges will anyway be not indicative of the performance in the bulk. And that is why we concentrate our efforts on studying the area filling methods in this lecture as well. So there are many methods, a few of which Professor Kapil has discussed in great detail. Among all of them are, say, grid cutting, pixel-based area filling using a mask, raster-based filling, direction parallel filling, contour parallel, spiral, medial axis transformation or MAT, a hybrid filling strategy, which may combine two or more of these strategies, continuous filling, and topology optimized area filling methods. And let us have a brief recapitulation of all of them one by one. Now, there are two main steps to convert the 3D model into the control data of an AM machine. And these two steps are slicing and toolpath planning. And those of you who have worked with a 3D printing machine or say a welding gun retrofitted to a 3-axis or 5-axis CNC machine, you will know that deposition, the movement of the deposition head is basically controlled by CNC codes, which is not very different from say the type of code you would write for any subtractive process. And just like for a subtractive process, you must plan the toolpath. So you must do for an additive process as well. Now, modern software packages abstract away a lot of these steps. Say a few commonly used and popular softwares are Simplify 3D, Ultimaker Cura, and similar. And there you just import your 3D model, you slice it as per your necessity. Often you will also have a library of machines to choose from, and the software will automatically recognize what are the tolerances, what is the least count, what is the build volume, and the build area of the machine, and it can even suggest you some optimized parameters. Say an optimized orientation in which you can minimize the supports. It will also, of course, generate the supports by itself. It will highlight the areas which might require supports. Of course, you are free to switch them off should you think they are not needed. But the point here being that these software packages abstract out a lot of these, say, processes that go out and that are working in the background. And as such, we are not really aware of how the toolpath is planned. What are the objectives that we must fulfill when planning a toolpath for successful deposition? What are the constraints it should satisfy, and so on. And this lecture specifically, will help us gain some greater insight into it. Of course, the end product of any such process which you see is, say, if you're depositing a cube, for example, in each layer you will say something like 2 to 3 such perimeter passes, depending on how many you specify, and then some infill. So a typical raster infill would look something like this. And if this is for the nth layer, in the n plus 1th layer, I mean, based on the type of variation which you have, if you give any interlayer rotation or not, you will again have something similar. In a sense, it will be 1 or 2 perimeter passes. And then the infill, say if you have a interlayer rotation by 90 degrees, in this case, the zigzag or bilinear filling pattern will resemble something similar to this. Now, what I'm showing by these straight lines are just the trajectory of the center of the deposition head. Of course, you will have material on either side, and there will be some step over distances. There will be interaction between successive layers that you deposit, which will ensure that your the area over which you're depositing gets filled with material to the specified density. Often, for when building solids, we want this density to be 100%. When building lattice structures, it will change accordingly. So let us continue. One more thing is, when you build the very first layer, which is in contact with, say, your build plate, you'll often find that the parameters that are used for the first layer are different compared to the parameters for the rest of the layers of the bulk. One change which you might have come across is that often in the first layer, for example, the print speed or the infill speed is only 90% of the specified value. And why this is to ensure that there is good adhesion and good deposition of the first foundational layer with the build plate. Once that is deposited, often depositing successive layers on that initial layer is less of a challenge. Often the major challenge is depositing that first layer and ensuring that it adheres and sticks to the build plate. Now, toolpath planning is a critical step of comparative process planning for AM, which influences the surface roughness, the dimensional accuracy, and the part strength of the printed parts. And it mainly includes the outer boundary, the inner boundary, the area filling paths in the boundary, and the area filling paths for the support structures. Because, as we discussed, often we would like the support structures to have lesser strength than the bulk so that they can be easily broken. Or we might like for them to be less dense and more porous so that we do not, say, waste a lot of material in building the supports because the supports are sacrificial. Or there might be cases where we simply print them with different material altogether, in which case again the process parameters will change as they are often suited for particular materials. And here we have the illustration of the different parts which are required in toolpath planning. So you have the inner boundary or the outer boundary or the exterior contour, the inner boundary or the interior contour highlighted in magenta here, and the area filling paths which you see in blue. And in this case, they are of the contour parallel type. That is, you have these paths which are almost following the contour boundary, and then you keep offsetting them towards the center, and you end up with these patterns. Of course, you'll find that based on the complexity of the geometry or the head spacing, the bead thickness, you might end up with areas which can have pores, like one here. Now, area filling methods uh, are available for both 2D and 3D surfaces. Of course, for 2D surfaces, they're well developed and well studied. In most cases, they are very well optimized. Whereas for 3D surfaces, it is still a work in progress and it is up and coming. So, as technologies progress, as researchers like you and I um, devote greater efforts toward developing such methods, they'll gain prominence. For now, we'll study mostly about 2D surface filling, and some of the common processes are grid cutting, uh, discretizing a surface into pixels, using a mask, or just your usually encountered path-based area filling. Now, each area filling method or each toolpath strategy must satisfy a few requirements, and they should be designed in such a fashion that they address certain objectives. What are some of these objectives? So, the few most important ones are listed here. One is to allow for quick heat dissipation and to prevent accumulation of heat. Now, we wonder why that is. So, in some of the AM processes, the material is added through melting the raw material and depositing on the substrate. Such examples may be, say, in DED or arc-based additive manufacturing processes, where you melt the material and deposit it. Even in some powder bed fusion type processes, the material may be melted. In others, they may only be sintered and you deposit it on the substrate. Of course, the way this works is the feedstock material gets melted. Also, a part of the substrate is melted, and both these melted uh, materials then solidify together based on their mutual solubility. They may even mix, and then they solidify to form the deposited bead in a process which is very similar to welding. Now, what this does is it causes the workpiece to heat up, and based on the thermal expansion coefficient, and if there is differential thermal expansion between the deposited material and the build plate, there can be significant warping. Even though you would typically fix your build plate to the build platform using, say, clamps or bolts, even then, even I personally experienced that depending on the type of geometry you're depositing, the amount of time for which a process goes on, and the temperatures which are involved, the workpiece can warp significantly. And what this means is that earlier you have planned your entire process for depositing on a flat substrate. So you're building just this cuboid, but now your substrate has warped. Now all your deposition or your toolpath planning, say you have sliced the structure using not even adaptive slicing, just uniform slicing. You have these uh, build layer thicknesses. But here, what happens is when you are building the structure, first, this contact at the bottom is no longer, say, a uniform contact. There is curvature involved. And then, based on whether the center of the plate bulges up or bulges down, the further calculations that you already put in place for the movement of the deposition head or the height by which the deposition head will move in each, say, in each successive print now no longer holds because it was relative to the base plate movement. We assume that here z is 0, and then you offset your head in each case, say H, 2H, 3H, and so on. But now, given that your build plate itself has moved up, those calculations are no longer valid, and there might even be the chance that your deposition head collides with the either the build plate or the pre-deposited structures. Thus, we should avoid warping to the extent possible, and this can be avoided by ensuring proper heat dissipation and minimal accumulation of heat. Now, care is to be taken during deposition to ensure that such warping induced distortions are at a minimum. Can we eliminate them altogether? Maybe not. But what we can do is ensure that they remain minimum. And the area fill strategy used should be able to dissipate the heat quickly and prevent accumulation of heat in any region of the slice. The second criterion is that the number of lifts should be minimum. Now, lift refers to uh, the phenomenon when, while printing a layer, your deposition head stops depositing, rises from the build platform, or it need not even rise, it stops depositing, moves to some other coordinate, and then starts depositing again. Now, this can happen for a variety of reasons. Say, on the same build area, you have multiple objects. So, say I have a cube here, I have a cylinder here, or I have something else, another block here. And the deposition head has to build all of these. So it cannot print continuously. Once it is done depositing a layer of one material, it has to go to the other object and then deposit there. So the travels in between these objects and then travel back in the next layer will involve uh, no deposition and only free movement of the head. These are called lifts. Why lift? Because often with such movement, the head might also move up from the build stage to prevent any collisions. And essentially, when we look at it, during such movements, we're not really depositing any material, and time is money. So these are often wasteful. If we can come up with strategies that minimize such lifts, then we'll be making maximum use of our time. The utilization ratio will be high, and our process will simply be more efficient. A second aspect is that during the start and stop of the material deposition process on a substrate, the process is highly unstable. You might also have seen this while depositing, say, even simple single beads on a plate. What we notice is that in the beginning, there might be such bulging of the bead. In the middle, it's almost uniform. And then towards the end, there's some bulging again. In some cases, the reverse also happens, whereas in the beginning and the end, you have under deposition, whereas in the steady state or in the middle, you have uniform deposition of material. Both of these cases are undesirable, but sadly, they cannot really be overcome fully. What we can do is minimize them. This can be minimized by minimizing the number of times the process switched on and off in a slice. Thus, attempt should be made to fill the entire slice area in a single continuous path from start to finish. A third requirement is the constant machine feed rate, because typically when you are building bulk structures with only one material, you would fix, you would optimize the process parameters, say the laser power, the scanning speed, the hatch distance, or the step over distance, and then you would keep this constant for every layer of the material. Thus, your energy density or material addition rate are constant. To ensure uniform properties, isotropic properties, and uniform deposition, the machine feed rate should also necessarily be constant. And if the material addition stays for a longer duration over a spot, excess material will get deposited, leading to unevenness in the layer and anisotropy in the materials. The fourth requirement being constant step over, where we need that the step over value should be constant in a slice. The distance between two adjacent scanning tracks should be uniform, and the actual value of the step over is determined from experimental trials, taking into consideration the optimal overlap. So typically you will have anywhere between say 30 to 40% overlap between successive tracks. And the way this is calculated is, as you were saying, so you have center to center distances, say you deposit one track and now you deposit the next with some overlap. Say this is the second track, and you would measure the center to center distances, say D, and this is a step over distance. And you can quantify overlap, say as some ratio, say it can be d by the thickness of the bead. So nominally your single bead is T thick and your step over distance or center to center distance is D. So you can quantify that D by T, and optimally this will be around say zero point 0.3 to zero point 0.4. Again, it depends on the process, the material and the machine which you're working. The first area filling method is called grid cutting, and as the name suggests, here you come up with a rectangular or Cartesian grid with which you divide the area or the region. The interesting thing this is the region which is not our region of interest. This is the region which we are looking to eliminate from the build. And it is especially useful in processes such as laminated object manufacturing, which typically utilizes sheets as the raw material, and two sheets are joined together with the help of, say, thermally activated or pressure activated glue. And a cutting process is used to separate the region associated with part and remaining region through grid cutting. First, you will have, say, a pass of laser or knife which cuts these exterior contour, and the interior contour. And then we try to divide the remaining region which we are not interested in into these grids. Similarly for the inner region here as well. Once we have the grids designed, we can simply use a laser or a knife depending on the material and pass the laser or knife over these grid lines and thus eliminate the unwanted material. A second method of filling the area is by pixel discretization. Pixels, as we are aware, are tiny areas into which we divide any surface, and depending on the size of your pixel, the resolution of your process is defined. So if you work with very tiny pixels, that is your unit area is small, you have better resolution, you can capture smaller features and more distinct geometries. Whereas if you work with coarser pixels or your unit area itself is very large, you have poor resolution. So typically in processes like digital light processing based VAT photopolymerization, binder jetting, and material jetting, the light projection, the binder injection, or the material injection respectively happen at the pixel inside the region associated with the boundary. Say for a binder jetting or material jetting like process, you have this deposition head which actually has many pores on the bottom side, and say this array of nozzles or pores can be corroborated to uh, a pixelation of the surface, and depending on this entire head will pass over your area, and depending on, say, if your head is somewhere here and we are looking at the top view, so on your deposition head the nozzles in these regions will be activated, whereas the nozzles in these other regions will be in an off state. That is, they will not release any material in the case of material jetting or any binder in the case of binder jetting. Depending on the resolution of your deposition head and the resolution of the tool path which you have planned for your deposition layer, you can have a less erroneous representation of the original curve, as we see here. So here in certain cases we have over deposition, and in certain cases we also have under deposition. The material curing and addition accuracy is governed by resolution of the pixels, which is a concept very similar to the DPI or dots per inch used in a 2D printer. If you print something with say 600 or 1200 dpi, the print quality comes out much finer. The graphics look very sharp. Whereas if you use a lower dpi, say 60 or 100, then the print quality uh, is poor. Another area filling method is by using a mask. So in some wet photopolymerization based processes, the entire layer can be cured by passing light through a mask. And when we say entire layer, this is because we are illuminating the entire layer at once using a floodlight uh, type of mechanism, say opposed to a process like powder bed fusion with laser source, where you have this laser beam which scans the surface point by point. You are suddenly illuminating the entire area at once. Of course, now we should take precautions or take necessary steps to avoid illuminating the surfaces which are not required for us. And this is ensured by using a mask. So either the mask can be created instantaneously depending on the requirements of each layer and by using the information obtained from the slicing data, or it can be made beforehand and used in process. The mask is basically a negative of the material deposited in a slice. So say if you want to have material deposited in the red region here, you would in your mask the red region, the region corresponding to the red region will be transparent. It will allow the light or illumination source to pass, whereas the rest of it will be opaque. The area filling here is creating negative of the slice. Of course, other considerations come into the picture, such as say just like the process of lithography, you can have a mask and say this is a hole in the mask through which you want light to pass. But it is seldom the case that light just passes in a very sharp fashion as a say a parallel collimated beam. Often you will have diffraction of light, and thus on your actual photoresist, the illuminated surface will not be say just the sharp shadow of the light, but it will actually be diffuse. Now this entire region is this was your desired region, whereas in reality this entire region is getting illuminated. Thus, we should design our masks and optimize the distance between the mask and the illuminated layer to minimize such diffraction effects. Now, another area filling method is the raster type of method, which is perhaps the most elementary, and we must have encountered it some way or the other. And here, what happens is your deposition head starts at one position, let us say it is point 1, moves parallel to either the x-axis or the y-axis, and goes to the other end of your contour to point 2. Now it will There will be a lift, that is, material will stop getting deposited. The deposition head might even rise from the surface. It will travel all the way back to the other side from whence it started to another point, say 3, and then again deposit material only in the positive x direction. And what we can clearly say is that this travel between point 2 and 3 in this case is very inefficient because we are not depositing material and we are using precious time to move to the other side of the surface, other side of the contour. Similarly, this raster scanning pattern can also take place along the y or parallel to the y-axis, or for a more homogeneous build with more isotropic properties, we can have an XY rastering scanning, or we can have some interlayer rotation across various layers. An improvement over the basic raster scanning is the zigzag method, and it is simply put forward to connect separate parallel lines into a single continuous pass, which leads to less build time and fewer transition motion. Also, since now we are not making multiple lifts and the print is not getting interrupted so often, the deposition will be more uniform, even though we might be well aware that while the tool head is making turns, the deposition quality varies. But still, we can say that it is better compared to simple raster scanning. And here we are making more efficient utilization of the time by starting from point 1, going to point 2. And rather than traveling all the way back, like in the previous case, here we start depositing, move to the next point 3, and continue depositing. Of course, the downside is that we are approximating this outer contour or the exterior contour by straight line motion of the deposition head, which will not be very accurate for complex geometries. And it is also mentioned here that due to discretization errors on any edge which is not parallel to the tool motion path, the outline is poor, leading to poor surface quality of the printed part. Depending on the chord height error between the exterior contour and your linear interpolation between the 2 points, you may also have certain voids which form there. And such a method is called direction parallel toolpath. It is one of the most commonly used methods in AM processes and consists of segments correspond to backward and forward motion in a particular direction within the boundaries of the cross section. You can also have toolpaths which are actually contour parallel, and this is a nature inspired concept. So it can be similar to the growth that you see in trees. So if you see any tree bark, you will have these rings which are almost, say, parallel to each other. Of course, in that case, they grow outwards from the center. In this case, it can be both ways. Either we start at the outer edge and come inside, or we start inwards and grow readily outwards. The contour path is applied by offsetting the contours of the geometry, and it creates series of offsets starting at the outer boundary and progressing towards the center. What we see here is that the step over is always maintained constant. Also, the number of lifts is minimized because here we are scanning this large line, sorry, not a line, this very long curve in one go without any lifts. Then we offset and then start again. However, the downside, as you might guess, is that for some complicated patterns, such as one shown here, you can have voids, as I am trying to highlight using this black ink. Thus, this contour parallel toolpath, it might work wonders for some geometrically complex patterns, but for other patterns, it might not be very suitable. For simple patterns, of course, it will work well. Now, all the closed loop outer contours in a slice plane are together collected in a pattern to be offset, and the toolpath has to be restricted in the area defined by the boundaries of the cross section. Another toolpath which has been used but which is not very popular is the spiral toolpath. Say if you want to deposit something like a circular geometry, this is still okay. But for most other geometries, this does not always work well. And I have found that even for depositing circular geometry, say you would typically have something like two perimeter passes. And then depending on your slicing software and your toolpath planner, either you start at the center and then deposit radially outwards. You start here again and or you start at the outer edge and move inwards. Of course, that will lead to more heat accumulation. The spiral path is very rarely encountered in actual practical applications. A more novel technique is the space filling path, which uses some optimized curves, such as the Hilbert curve, Yano curve, to fill cross sections in a layer. Some examples are also illustrated below. And what these achieve is that the offset is always constant. The number of lifts is minimum, and often it may be planned such that even the heat accumulation is at a minimum. Another method is MET or medial axis transformation. This is another nature inspired concept. And what we are trying to do here is just like in our human bodies, we have a skeletal structure on top of which the muscles and all the organs are organized into our body, which gives us strength. Similarly, for a complex shape, we are trying to come up with the skeleton of that shape, and then we try to distribute the material around that skeleton to end up with the final profile that is needed. How this can be accomplished is that for every pair of edges, we draw circles to which these edges are tangents. And at each point, we are trying to fit the largest circle. We collect its center, say C1. At a later instant, we have another circle, C2. Similarly, you can see that for these two pair of edges, a circle can be drawn. Maybe its center is C3. And we continue this exercise throughout the material. Here the circles will diverge again. So you can have one circle for this pair, another for this, and we keep collecting their centers. Once all the centers are collected, we join them to come up with the medial axis or the skeleton of the structure. Once you have the skeleton, you simply offset it till you reach the exterior contours and your toolpath is achieved. Why this is important is because traditional toolpaths like contour cannot adequately cover the geometries of parts and may leave certain voids or undesirable gaps. And if the contour depicts a geometry of the boundary, the image is shown in the figure, also called a skeleton, and it describes the domain shape based on the medial axis and bisects the domain to get the skeleton of the inner geometry. It is especially useful for very complex domains, such as one shown here. Yes, so the same geometry, which had certain voids when filled using a contour path or contour parallel technique, when filled with a medial axis technique, we can see that the number of voids has been minimized. The most versatile, of course, will be a hybrid path where you combine two or more techniques to come up with a toolpath plan. And this is also perhaps what is most commonly implemented in commercial 3D printing software packages, where say for the inner and outer perimeter, you have a contour parallel toolpath, whereas for the interior, you have a zigzag. Now you can also have continuous paths where you simply do not, you start at one point and you print the entire layer in one single go without stopping and without any lifts. Why you would like to do this is because during the start and stop of material deposition, the process is highly unstable. As we discussed, there can be over deposition or under deposition. To prevent this, the number of times the process is switched on or off in a slice should be minimized. A continuous path where we have zero lifts can fill the entire slice area in a single continuous path from start to finish and also eliminates the air passes. Air passes being when your head is not depositing, it moves up from the bill plate or previously deposited layer and moves to the other coordinate where it resumes deposition again. Here you have some such examples. A continuous direction path, a continuous hybrid path utilizing both raster and contour path, and a continuous fractal path, which actually used some complex shapes to print this very complex geometry of India. The area filling methods can also be optimized based on the topology that you need. And these are, of course, these topologies extend to three dimensions. A few common examples are also illustrated here. We have the honeycomb structure here. As we know, the honeycomb structure is very strong in compression. Again, it is another nature-inspired structure. You have the gyroid structure here, which is, say, commonly encountered in biomedical implants. Depending on the desirable level of porosity, you can have these others such as across 3D, triangles, trihexagon, cubic, and so on. And of course, as we can estimate, each of these will have, say, different strengths and weaknesses. Some might be more isotropic than the others. Others might be more suitable for directional properties. They may help to vary the porosity and so on. However, all of these methods are for 2D surfaces. What happens when we want, or planar surfaces? What happens when we want to fill a 3D surface? That is a free-form surface, which is not generally lying in only one plane. Now, three main types of area filling methods are given for reference. We'll not study them in depth because they are still up and coming. They're not standardized. They are the direction parallel type, the contour parallel type, and the space filling curve type. So each of these are simply extrapolations of the techniques we studied for 2 dimensions to 3 dimensions. Let us quickly look at the other set of slides as well. So in this week, we also started with an introduction to liquid additive manufacturing methods. As Professor Kapil has pointed out in his lectures, ASTM gives a categorization of additive manufacturing into 7 types of or 7 categories of processes. However, for the purpose of this course, we are following categorization based on the feedstock type. So based on whether it is solid, liquid or gas, we'll classify the processes and study them one by one. We are starting with liquid additive manufacturing. We will look at the classification of slicing methods, whether they are direct or indirect, whether it's uniform or adaptive, whether it's horizontal or conformal, and uniform slicing of STL files with control determination and organization, and adaptive slicing of STL files. I think this content has been is erroneously put here. It belongs to some other module. Let us ignore it for the moment. Yes. Now, ASTM has classified all additive manufacturing processes into 7 broad types. And as we discussed, they are ordered in terms of higher, say, energy requirements. So, watt photopolymerization will typically utilize the least amount of energy. Say it will have a UV source of the order of 40 milliwatts. Whereas when you approach powder bed fusion, so 2, 3, 4, powder bed fusion typically utilizes, say, a laser of the order of 500 watts. For DED, you can have anywhere between say 3 to 8 kilowatts. At IIT Bombay, in our lab, we have a 5-axis hybrid additive manufacturing machine, which is a laser wire DED machine, equipped with a 3 kilowatt laser head. We are looking to augment it even further. And a liquidum process uses the liquid form of raw material. So it will typically relate to either wet photopolymerization or material jetting. One would ask, why not binder jetting? Because in the case of binder jetting as well, we are dispensing some liquid material through the deposition heads. However, the requirement is for the type of the raw material. We are well aware that in binder jetting, the raw material is already present on the bed, and it is spread by a recoater or a roller, and it is only the binder that we are further depositing using the head. The raw material is still in powdered solid form. Thus, it is not a liquid based in process. From this flowchart, we'll be looking at mostly these processes marked 1 and 2. So, for the type of raw stock, which are liquid and which may corroborate to either photopolymer or to rapid freezing. When we are talking about photopolymerization, the working principle is perhaps very similar to the basic polymerization process, which most of us would have studied in elementary school. We start with a mixture of a photoinitiator and a monomer. As the name implies, it is still in monomeric state, that is, it is not linked with other monomers, which finally forms the polymer. When such a mixture is irradiated with energy, which is denoted here by H nu, H being Planck's constant, nu being the frequency, this energy is absorbed by the photoinitiator, it gets excited, and it generates a free radical, which is shown here by these red dots. Now, upon excitation, these free radicals can then be passed on to the monomers, as we see here, and a chain is formed. Now, these are spontaneous processes and can happen suddenly and across many such pairs. This free radical chain now propagates. That is, the monomer passes this free radical onto the next monomer, and from there it continues moving forward in a sort of chain reaction, as is shown here. This step is called chain propagation. And once no more uh, free radicals are left in a region, we have chain termination. This here we see a few complete chains, say similar to this. Now, such a photopolymerization-based liquid AM process builds object by photocurable liquid resin that cures or hardens under exposure to UV light. The UV light scans the cross-section of each slice to selectively cure it. And after complete curing of a layer, the build platform may be moved either down or up, depending on whether your build direction is along the positive Z, along the negative Z, or if there is no fixed build direction at all. After this, the next layer of liquid resin spreads over or below the previous layer, and the process continues. The whole object is built by repeating the process for each layer, and the uncured liquid, which has remained in the liquid state, is removed from the vat, and the object may proceed for further processing. There are various subsystems involved in the working principle of such a photopolymerization based liquid AM process. Number one is the type of liquid itself. What are its properties? What amount of energy does it require for, say, polymerization to initiate? Whether it is transparent or not? What is its viscosity? And so on. Second is the type of illumination, which will be a UV light. So whether it is uh, say very well focused and collimated into a small area, something like a laser beam, or whether we are illuminating the entire layer at once using a floodlight or similar mechanism, the type of scanning system, whether the UV light head moves, or whether the stage or vat filled with liquid moves, or whether it is a combination of the two, say 2 degrees of freedom are with the platform, 1 degree of freedom is with the stage, with the deposition head, or so on. The build direction, as we discussed, whether it is along positive Z, along negative Z, or whether there is no fixed build direction at all. And finally, the recoating system. We'll just discuss each of them briefly. Now, the scanning system can either be galvanometer based. Galvanometer consists of a pair of mirrors. 1 second, please. Yes. So, galvanometer consists of a pair of mirrors. These mirrors are connected to motors, and based on the combined motion of the two mirrors, you can deflect a beam of light across the entire region of interest. Now, typically these mirrors will have very low inertia, which means then that you can actuate them at great speeds. And by suitable motion of the two mirrors, you can cover the entire region of interest and cover it at a good speed. However, the scanning is still point by point, and thus it requires some finite amount of time. The second can be the flying liquid, where say you have a deposition head which moves, and this has several nozzles from which the liquid is dispensed. And depending on, say, the area of the layer to be deposited, the area of this deposition head, the nozzles, the pixel resolution, the head will move, say, a finite number of times over each area. Say, if we are looking at the top view, this is the area of the total region of interest over which, say, my structure is deposited, to be deposited, and my head, say, is this big, then it will cover this region at once, deposit material in all at all these points. Then it will move by this finite distance. So now it will come here somewhere. Again, repeat the same thing. And here we can see that in approximately say 3 steps, it can cover the almost the entire region of interest. Of course, this is also accompanied by at the back by a curing mechanism. So you have a UV laser, mostly UV floodlight, which is fitted to the back of this head, so that while during the next deposition, the previous deposition is already getting cured almost instantaneously. Again, the optics can be flying. That is, the liquid remains constant in the vat, or it remains stationary in the vat, whereas the optics or the laser or the UV floodlight itself is moving over the entire region. It can also be DLP based. DLP stands for digital light processing, where you have an array of mirrors These mirrors are typically called micro mirrors, so they are of the micron range. I am drawing them in an exaggerated fashion. Of course, the gaps between successive mirrors will not be so high. And just like dividing your region of interest into pixels, you divide this entire mirror into these tiny micro mirrors. You actuate them using, say, electrical coils. And depending on which mirrors are activated and which mirrors are still in an off state, the region corroborating to these mirrors will get illuminated and cured. Of course, another scanning system is simply the mask, which is illuminates the entire surface in one go. This process is almost instantaneous because you are curing the entire region of interest at once. So it will always be faster than any other raster scanning type pattern type process, such as one utilizing a galvanometer or a flying liquid. A second subsystem is the shape of the UV light. So it can either be in the form of a laser beam, that is, you have one very sharp beam which illuminates the surface. Of course, utilizing something like galvanometers, we can deflect this beam over the entire region and cover the region. Or you have the floodlight, where you are simply illuminating the entire region at once. You are filtering out the undesirable and desirable regions utilizing a filter. Depending on the type of photoresist, whether it is a positive photoresist or negative photoresist, the suitable area will get cured. Now, another problem with the laser beam type shape of UV light can be whether the exact profile of the beam is getting maintained or not. And what typically happens is that, say, when you are depositing just below the laser light, or when the angle of deflection with the vertical is very low, the beam is still maintains its circular profile. Whereas when you're depositing far away, the beam in such a case may have an elliptical profile, and that is because the beam is expected to have a constant profile along this sphere in 3D space. However, when you are reaching far regions on the flat bill plate, you are moving away from that sphere, and thus it is expected that the profile of the beam may change. This, of course, leads to a, say, variation in energy distribution. And typically, for laser beams, you will have something like a Gaussian distribution of energy. But when you're changing the beam profile, the distribution will change. It will also lead to, say, variation in the bead sizes. Even anisotropy in properties may result from this. Whereas from the floodlight, it is expected that the properties in and the build characteristics in the same layer will be uniform. Of course, we'll have to look out for diffraction based effects that we previously discussed. The very shape of the liquid itself, where you can either have the liquid in a vat, so you have this tub like structure which is full of liquid, and depending on, say, your build platform and your build strategy, whether it is along the positive Z direction or the negative Z direction, the process dynamics will change. Or you can have the liquid getting deposited in the form of jets, which we just discussed. Say you have a print head which is full of nozzles, and those nozzles can selectively deposit tiny droplets of liquid material in the desired regions. The build direction can either be along positive Z or negative Z, or it need not be fixed at all. It can be highly variable. And each of these offers its own set of advantages and disadvantages. In the case where you have, say, for example, a wet type of shape of the liquid, and you have a positive build direction. So each time your stage will move down by the pre-decided specified height, which is called the layer height, and the build will progress for the next layer. When your build direction is along the negative Z, in each step, your build platform will actually move along the positive Z direction, and the build will progress. And one or a couple of very obvious advantages that you can foresee here are that if there are such hollow sections in your build, in the case where the build height is along the negative Z direction, because of the action of gravity, any remaining liquid uh, uh, photopolymer will automatically get drained out of this, uh, say, hollow region. Whereas for the case where we are depositing along the positive or building along the positive Z direction, there is a chance that the liquid photopolymer might get entrapped in this region here. And any successive curing of another layer on top of this may lead to it getting trapped. Again, a second thing which we can see here is that, okay, maybe we'll discuss it in the subsystem of recoating. The third type of build direction is a variable direction or no fixed build direction at all, where you say you are still working with a vat of material and you have a flexible energy source or a flexible robotics. It changes its direction, which has multi DOF in space, and it changes its direction with each build layer so that the shape of the structure changes as well. I also have a video on this, which I'll show you, and it's pretty interesting. Now, the types of recoating system. One can be deep dipping. In deep dipping, what happens is after each layer is built, your build platform, along with the deposited layer, gets dipped into the bulk of the photopolymer so that you accumulate a good amount, a healthy amount of photopolymer on top of it. Now, this will again rise to the top, and something like a doctor's blade will scrape off the excess photopolymer from top of this, and only the desired thin layer of photopolymer will remain. However, to allow for this deep dipping, you still need excess quantities of photopolymer in the vat. A second type is called top feeding, where after each uh, layer of deposition or each layer of curing, you have a flying liquid head which comes on top of it, deposits the material in the necessary regions, does not deposit material in the regions which are not to be cured, and then moves away. This is called top feeding. It can be accomplished by a nozzle, micro nozzle. The third, of course, is called bottom feeding, where, say, if we discuss similar to the previous case, we are building along the negative z direction, in which each movement of the build plate along the positive z, you now have this tiny space at the bottom which needs to be filled with resin. Now, this can be accomplished in multiple ways. It can be accomplished via gravity, that is, we simply move the stage up by some distance and the fluid will flow into place. However, if the region is very tiny or the fluid is very viscous, it might not be possible to accomplish this on its own. So we can also use some sliding or rotating type of mechanism, and we'll take a look at this in further lectures. Now, based on the combination of the scanning system, the shape of the UV light, the shape of the liquid, the build direction, the recoating system, different liquid AM technologies have come up, and a few of them are highlighted here. So, if it uses a galvanometer based scanning system, a laser beam as the shape of UV light, a liquid vat, builds in the positive Z direction, and utilizes deep dipping for recoating. The process is actually 3D Systems SLA, or the very first 3D printing system which had been developed. Similarly, depending on the combination of the other subsystems, the process may be changed. For example, 3D systems changed from deep dipping to top feeding, and this new technology was called SLA, Zephyr. Similarly, based on the other combinations, other technologies have been developed and they will be discussed in future lectures. I see Dr. Thangapandian has raised
Yeah,
his hand. Yes, sir,
yeah.
please
Can
continue.
can you elaborate the flying liquid and flying optic system? It's
Okay, the flying liquid we already discussed, so I'll show again. Yes. So the flying liquid is what happens when you have this deposition head. And if we look at the bottom view, so your head has these array of nozzles. Of course, the density of nozzles corresponds to the pixel density on your build. And what happens is this entire head will move over the area of interest. Say in one case, it was at position 1. It deposited material wherever it was needed, say within this contour. Whereas in all other regions, the material was not deposited. Then this entire head will move further down to a new index position, say position 2, and it will repeat the same exercise. It will deposit the material in the required regions, and there will be no deposition in the other. Why it is called a flying liquid is because we are moving the entire, uh, say, liquid vat, or in this case, the liquid microchannels over the region of interest and depositing.
so we are
Similarly, the entire vat
depositing
might
the
also move.
actuators or photopolymer.
No, sir, we are actually moving the liquid feedstock itself. That is why it is called flying liquid.
Okay, okay.
Yes. In some cases, even the entire vat of liquid might move. So you say you have this vat in which the liquid is stored. Your laser head is fixed. Say it is only shining the laser at one location, but you are moving this vat along the XY plane. Similar to, say, a DED process where the deposition head is fixed and the XY motion is with the stage itself. Of course, we can foresee that such a type of system will have large inertia associated with the movement of the liquid. There can be surface waves, there can be other perturbations, and thus it is not always recommended. However, there might be a few cases where this is implemented. So we'll also solve a few questions related to these topics, but let us break for a few minutes. So I'll see you again in about 5 minutes or so. Thank you. Hi and welcome back. Thank you for your patience. So let us quickly look at the video I was talking about, and then we'll continue with the questions. So yeah, first this video of a 3D printed basketball. Now, Wilson, as some of us might know, is a renowned company in sports. They make they are famous for their tennis gear and their basketball gear. I'll just play it again, and we see how this basketball is actually hollow. It has been designed to match the performance of an actual NBA ball, and it might have used technologies such as non-conformal slicing, conformal slicing, sorry, and control of porous structures for building this basketball. Just look at the next one. Yeah. So this, after having talked about support structures and build directions for so long, we see an example of this, where it's as if we are building in free air. There are no support structures, and there is no illusion. It's not like there are some invisible, say, strings or something holding it. This is a live process that we are seeing. We are building large overhangs, even a completely horizontal part, and this is happening in real time. This really shows the pace at which additive manufacturing technologies are growing and developing each day. So yeah, pretty spectacular. In case someone wants to find out more about this technology is called direct writing, and depending on the control of the chemistry of the filament material and the energy source, it is indeed possible to build overhanging structures in space with variable build directions, just like we were discussing. So the build direction need not be fixed along the positive or negative z at all. Now let us continue with our tutorial questions. So, okay. Yeah. Now the objective of these tutorial questions is to actually help you solve your assignments better, and also to say revise and reinforce our concepts. Often you will find that the questions that we discuss in these sessions are somewhat similar to the questions that are posed in the assignments. Of course, the values will be changed, and if you can work well through these tutorial problems, it's my expectation that you will be able to solve the assignments equally well. The first question says a rectangular and square contour of given dimensions are fabricated using the laminated object manufacturing process from a square sheet of dimension 10 centimeter cross 10 centimeter. Calculate the ratio of the area of the unwanted material for the square to the rectangle. So we have a laminated object manufacturing process, and this is our feedstock material, which is actually a sheet 10 centimeter by 10 centimeter long. And in one case, we are trying to fabricate a rectangular section, which is say some 8 cross 3. So maybe something like this. In the other case, we are trying to make a square of say 5 by 5. And in each of these cases, the remaining area of the sheet will have to be eliminated. This is the unwanted region. And we are asked to find the ratio u square to u rectangle of the area of the unwanted material. So let us do it. Let us first calculate the unwanted material for the rectangle. The area of the desirable region in this case is 8 into 3 centimeter square, which is 24 centimeter square. The total area of the sheet feedstock is 10 into 10 or 100 centimeter square. Thus, the area of unwanted part is 100 minus 24 or 76 centimeter square. Let us repeat this exercise for the square region. Again, the desirable region has an area which is 5 cross 5. The total area of the sheet feedstock is 10 cross 10, which is 100 centimeter square, and therefore the area of the unwanted region is 75 centimeter square. We asked to find u square by u rectangle. For u square it is 75 centimeter square. U rectangle is 76 centimeter square, and this simply comes out to be 0.9868. This is the desired quantity that we were looking for. Let us move on to the next question. A cube of dimensions 20 cross 20 cross 20 centimeter cube and a cuboid of dimensions 5 cross 10 cross 20 centimeter cube have infill densities of 40% and 60% respectively and are fabricated using the FDM process or the fused deposition modeling process. We have to calculate the ratio of the volume of the infill material. Now, as we discussed, that we might have the tool path which can be topologically optimized such that the infill density is not 100%, but it can be varied depending on the requirements. Here we are told that the infill density is 40% and 60% respectively for the two cases, and we are asked to find the ratio of the volume of the infill material. So again, let's first do it for the cube in this case. The nominal volume of the cube is 20 cross 20 cross 20, which is 8,000 centimeter cube. The infill density, however, is only 40%. How can this be achieved? Say in each layer, you deposit these two perimeters, outer and inner, and then you deposit it via some zigzag. Now, the step over, depending on the bead width, and depending on other process parameters, there might be some gaps here. So if we are to show the bead itself, can look something like this. All of this remaining region is actually not filled. Of course, this is a very exaggerated view, but you get the general idea. That is by modulating the overlap, by modulating the hatch distance, the step over the toolpath strategy, we can change the infill density that we achieve. Now, now that we know that the infill density is only 40%, we know that only 40% of the nominal volume is actually built with the build material. The rest of it exists simply in the form of voids or gaps. Therefore, the ratio of the volume of infill material V cube in this case is simply 40% of the nominal volume, which is 3200 centimeter cube. Let us repeat this exercise for the cuboid. First, the nominal volume of the cuboid, 5 cross 10 cross 20. So that to be 10,000 centimeter cube. The infill density in this case is 60%, and thus we know that the volume of the infill material, which is denoted by V cuboid, is 60% of 1000, which is 600 centimeter cube. And we have to find V cube by V cuboid. So that 200 by 600, which is 32 by 6, 16 by 3, 3 5 is 15, 5.33 approximately. And this is the quantity we set out to find. The third question is asking us, what will be the difference in toolpath strategy for exterior contours obtained from direct slicing and indirect slicing? So I would like to take us back to the previous session where we discussed these concepts of direct slicing and indirect slicing. Direct slicing is here where you start with the exact CAD model and you slice the exact CAD model itself and obtain these contours, which in this case are the exterior contours. And for this given example, where we have the exact CAD model of a sphere and we slice it via the direct route, we end up with a contour which is a circle. In the case of indirect slicing, again we start from the exact CAD, but the slicing operation does not take place on this exact CAD model itself. We first transform it or convert it into an intermediate STL. And now we no longer have the exact geometry with us. Now this is an approximation of a sphere. Of course, if we use, say, very small triangular elements, we will eventually approach the actual sphere, but it will always be an approximation. And now the slicing operation takes place on this intermediate STL, and the contour that you end up with is a polygon. Of course, for a polygon with very large number of sides, you will end up approaching a circle, but it will never be exact. And this is the difference between indirect slicing and direct slicing. So how will the toolpath change? This was also discussed by Professor Kapil in the lectures. So for the case of indirect slicing, we first find the intersection points of the slicing planes and the tessellated triangles. Once these points are obtained, we can simply interpolate between these points using lines or a linear interpolation. And this is good enough because we are anyway working with an approximate geometry of the object. And this will give us the contours. However, in the case of direct slicing, now we are working with the exact CAD model. We again find the intersection points. However, now even though the intersection points are known between the slicing plane and the actual geometry, we cannot simply join these points by straight lines or using any linear interpolation. We must interpolate using higher order functions. One example can be, say, polynomials, but there can be other families of curves, and then we end up with the contours. The fourth question is asking us to spot the odd one out in the context of area filling methods for toolpath planning. And the options given to us are laminated object manufacturing, stereolithography or SLA, binder jetting, and DED. And as we have been discussing, laminated object manufacturing is pretty unique in the sense that it is perhaps the only method in which we devote most of our energy into eliminating the unwanted regions. In most other methods, we will be planning the toolpath for the desirable region, how to fill that region with area filling, how to make proper and exact contours for it, and so on, how to minimize gaps, how to ensure proper heat dissipation. But perhaps laminated object manufacturing is the only method where we are more focused on eliminating the unwanted regions. So say this is my desirable region, and we are starting with this sheet feedstock. Now we will draw grids, superimposer, Cartesian rectangular grid on this unwanted region. And using a suitable laser or a knife, depending on the type of feedstock material, we will then eliminate all of these unwanted regions. Say we can simply run the laser or knife along these grid paths, which will end up eliminating this unwanted material in the form of small cubes. And because of this, say, standout feature, where we are devoting most of our energies on actually working with the undesirable region rather than the desirable region, it is the laminated object manufacturing which stands out in this case in the particular context of area filling methods. In all other, of course, we are more interested in the region of interest, whereas here we are more interested in the unwanted material. Next question is asking us on the basis of sensitivity to ultraviolet energy source, what is the type of photopolymer material generally used in liquid AM processes? Is it a positive photoresist or is it a negative photoresist? So some of us would have had exposure to, say, a course that dealt with optical lithography, but I would still just briefly revisit the concepts involved. So in lithography, we have a substrate on top of which we apply this photoresist material, and then we place a mask on top of this and expose it to a suitable radiation. Now, the mask has certain gaps in between, which are the features, and through these gaps, the light selectively enters. In all other regions, the light is blocked. Thus, we see that only the selectively uh, selective regions on the photoresist are exposed to the incident radiation. Here they are highlighted in gray. I'm also shading it in black. So we see that the region in blue was not exposed to any energy. The region which is in gray and black was exposed to energy. And what can happen is upon the chemical machining process or the chemical machining step, depending on the type of photoresist which we had used, either the exposed region will get washed away. In such a case, the photoresist is said to be of the positive type, or the exposed regions will survive, whereas the rest of the photoresist will simply wash away. In this case, the photoresist is said to be of the negative type. Now, if we recollect our discussions on the type of, say, wet photopolymerization and other liquid based processes, where we use a mask. So, what we saw is that, say, if this is the region that I want to eliminate, want to deposit in a layer, my mask will actually look something like this entire region will be, say, opaque, and this region will be transparent. Thus, what we see is that we are exposing the region of interest to energy radiation, which in this case is ultraviolet rays. However, this is common to both positive and negative type of photoresist. Also, the exposed region gets cured while the remaining liquid, say, is removed at the end of the process. And thus, it was the region which is cured, which turns out to be our desired region and which survives. Thus, the photoresist is of the negative type. Here also we see that the region which was cured selectively is the one which survived and went on to form the features. Thus, the type of photoresist may be said to be analogous to the negative type. The sixth question is asking us, during deposition of a material in a single layer, there are certain steps at which the process becomes unstable. Which of the following are such steps? Is the start of the print a step during which the deposition process is unstable? Yes, it is, because it is governed by inertia. You are suddenly extruding material from a condition of no extrusion, and thus it is expected that there will be either some over deposition or some under deposition. We have also looked at the case which is similar to, say, deposition of a weld bead, where we find that at the beginning the bead bulges, in the middle it is quite uniform, and at the end it bulges again. Of course, rather than a bulge, it can also be a dip. That is, you have under deposition at the beginning and at the end. Thus, both the start of print and the stop of print are, uh, say, regimes in which the process does become unstable. Turning a corner in the toolpath. Now, from our basic understanding of mechanics, what we realize is that if the head is moving, say if you are just printing a square and we deposit it along this line, and now we have to turn. The velocity of the head will change. Even if the speed remains constant, the direction is changing, which implies change in velocity, which in turn implies and is implied by acceleration. Thus, there must be forces involved which actually lead to this acceleration. And typically, what you will find is that when the deposition head is heading into a corner, it slows down, just like a race car, or just like even during our normal driving when we are taking a turn. When we approach the turn, we slow down, and when we have completed a turn, we exit fast. Once the turn is completed, the head will move away quickly. Thus, in this time, because of the change in speed, or you can say even almost a sudden stop-like motion, which is stop-like regime, which is achieved at the corner itself, the process becomes unstable. And how this materializes in a build is that, say you wanted to print a cube, but you'll find that the ends are bulged and it's almost like there is a dip in the center. Also, the corners will not be sharp. Thus, we can see that Even when the head must turn a corner in the toolpath, the process becomes unstable again. Change in Z height of the deposition head or build platform. Now, we know that whenever the deposition head, or in some cases the build platform, is switching to the next layer uh, by changing the Z height by a constant distance known as the build height or layer thickness, there is no deposition ongoing. That is, deposition first ceases, the head moves away from the stage, and then the change in Z position takes place. Thus, since the material itself is not getting deposited, the process cannot be considered to be unstable. We are looking only at processes or regimes during deposition in which some instability is introduced. So options A, B, and C are correct in this case. The next question asks us, what are the advantages of bottom feeding method in wet photopolymerization? Just to recollect, we looked at two types of feeding method, actually more, but here we are comparing bottom feeding to the other. So there was one where you had your regular top feeding. In the other case, you have the bottom feeding. And for the case of this deep dipping, what we observed is that every time the build platform and the pre-deposited layers must be dipped deep into this vat of liquid so that an excess amount of resin comes on top of it. Then a doctor blade or a roller-like mechanism will scrape off the excessive resin and will only leave the necessary amount of resin on top of it, which will again then be selectively cured. Thus, we require a large amount of resin in the vat. Whereas in the case of bottom feeding, we see that the height of the resin column needed simply equals the layer height. As long as you have just enough resin of a height corroborating to this layer height within the tank, or whether you can pump it after each Z movement of the build stage, you are good to go. Thus, definitely less resin is required compared to top feeding mechanism, better accuracy and finish. Now, accuracy and finish are not always decided by how you're feeding the resin. It is more dependent on the layer height itself, and we can choose the same layer height, whether it is a bottom feeding or top feeding process. It will also depend on the toolpath and the slicing, the approximation into an STL file or not, or whether it is a case of direct slicing. The finish will again depend on the process, machine and material combination, on say how well the parts got cured, what were the energies involved, if it was a laser scanning mechanism, whether the profile got deviated from the design profile or not, and other such factors. The feeding alone cannot determine, and thus we cannot conclusively say that better accuracy and finish can be achieved by bottom feeding instead of any other type of feeding. Less chances of entrapment of uncured resin. This is something we already discussed. Say in this case, there is a chance that in this hollow section, the resin which is present may get trapped when the next layer is built on top of it. Whereas in the case of bottom feeding, because of the action of gravity, any resin which might have remained in this hollow section will simply move out whenever the Z stage is moved. And if resin is not desired in that region, it will not get trapped. Of course, there might be some capillary action where from the neighboring wall or from the next layer, some resin has crept into this hollow section and might end up getting secured over there. But still, to a large extent, we can say that the chances of entrapment of uncured resin are highly minimized. Thus, options A and C are correct. The eighth question is asking us, how can existing CAM packages be used for area filling of a 3D surface? And this was mentioned by Professor Kapil in class. So, how we adapt these existing technologies or the existing infrastructure to suit our additive needs is that, say you have an existing CAM package. Here we extract, say, the machining strategy. Now, this will be in the form of a toolpath, which is generally a G code, consisting of various G and M codes, which corroborate to various tool commands. And we modify the G code as necessary. For instance, we will add laser head on off commands. We'll add relay checks to see whether the laser has turned on off or not. We'll introduce certain warnings, see if the material is getting extruded in the case of wired AD, whether there is any contact error or not, and so on. And essentially, what we are doing is the original CAM package is geared towards removal of material. From that, we will repurpose it towards the addition of material. Of course, it is, say, more involved and more complex than how I've mentioned it here. But this is the strategy which is used to adapt existing CAM packages for additive needs. The next question is asking us, how are individual mirrors of a DLP or digital light processing system manipulated? Is it by using galvanometers? Is it by use of electromagnetic coils? Is it by applying any contact forces, or are springs involved? So let us just refer to the actual structure of a DLP mirror system. And I have borrowed this from Professor Kapil's slides, which you'll encounter in upcoming lectures. So a DLP mirror actually consists of many micro mirrors. Here we have some relevant terminology related to them, such as the micrometer size and the micrometer pitch, which is the distance, center to center distance between two adjacent mirrors. There is also a small region in the center of the mirror called a via, which is not does not actually reflect light. However, this given that this region is very small compared to the area of the mirror as a whole, our print performance is not affected to a great extent. Now, on the right, we also see a schematic view of the mirror, where we see that the mirrors are always at certain angles, say at -12 degree or +12 degree. And depending on the relative position of the build platform and the micro mirror array, we see that in one case, which is said to be the nominally on state, the light is incident or the energy is incident on the mirror. But given that it is inclined at an unsuitable angle, the radiation is again, rather than getting incident on the build platform, it is reflected away. Whereas on in the nominally off state, the light or the energy which is incident is then getting reflected towards the build platform. And this actuation is achieved by using electromagnetic coils, as we already discussed. Galvanometer is a scanning system which uses a pair of mirrors for quick deflection of the incoming beam, and it has very low inertia, thus we can have very quick scanning. No contact forces are involved here, and neither are springs. All actuation occurs using electromagnetic coils. The 10th question is asking us, what are the disadvantages of a galvanometer-based liquid AM process? Are the scanning speeds low? No. We already discussed how, given that the galvanometer mirrors have very low inertia, we can achieve relatively high scanning speeds. Are the production times high compared to, say, an area illumination or a floodlight method, where we illuminate the entire area at once rather than scanning with a laser beam? The production times will be high because even though we can deflect and scan really quickly, we are still really scanning it point by point. That is, we are scanning very small areas at a time compared to, say, an area filling technique, which is almost instantaneous in the sense that it illuminates the entire region of interest in one go. So, yes, it may be said that the production times are higher considered to other scanning type AM, liquid AM processes. Low accuracy. This is not true because, as we know, that the laser beam is highly collimated and can be of very fine size. Depending on the size of the laser beam, we can achieve very high accuracy. Also, we know that we can actuate the galvanometer mirrors very precisely and can cover layered areas. Thus, the accuracy is good. The change in beam shape away from the optical axis. This is something we already discussed during our lecture today, that near the optical axis or at small deflections from the optical axis, say something like this, the beam profile is still circular, and it will remain circular if we are to move it along this sphere space. However, our substrate will mostly be a flat region, and thus when we are scanning areas that are far away from, sorry, that are far away from the optical axis, there is a high chance that there is a distortion in the beam profile and the beam shape, and from circular it turns elliptical. This is referred to as stigmation error. We'll also discuss more about it in the upcoming sessions. Thus, the change in beam shape away from the optical axis is another consideration which amounts to a disadvantage, and thus B and D are the correct options. I see that I have exceeded the time for our session. I apologize. Um, Thank you for tuning in, and I'll see you all next week. Thank you.